Morning. We're going to take a look at reaction types today. So this is the reaction types part of the unit, and in the following sections of this unit, we'll be learning a little bit more about how reactions work and be able to ultimately predict how reactions are going to go forward. So what we're going to do is go through the day one notes and see if we can make sense of what reactions are and how they behave. So what's always been fascinating to me about chemistry is that, you know, it's so connected together. All the parts you know, are related to where the electron is and what the electron's doing. That's really what chemistry is all about. And in that idea, there's all these different things that can happen. And for us, those show up as different reactions. Okay, so the ones we're going to look at and identify today, and this is just the major reactions. You know, there's other types of reactions, but this will cover you for most, you know, normal circumstances. So we have a subgroup too. So there's 5 plus a subgroup. So we have synthesis. We'll be doing that next week. We'll be looking at synthesis reactions. Then the opposite of that is decomposition. Then we have single and double replacement reactions. And acid-base is a subtype of the double replacement reactions. And then we also have combustion reactions with burning, you know, different fuels. So let's take a look at synthesis reactions a little bit more in detail. So synthesis reactions, or combination reactions, as they're also known as, are reactions where you have two reactants come together. Now, if you remember before in the previous unit, we talked about reactants and products. So reactants are the things that come before the arrow, and products are the things that are created after the arrow in a chemical reaction. So here is an image where we can see our reactants are a starving bird, and you know, it sneaks up and finds this gigantic worm, I guess, that's like almost the same size as itself, and it eats it up, and it becomes automatically, awkwardly obese, right? And has a belly button as well, which is disturbing for a bird to have a belly button. But you get the picture here that the two of them came together and created one thing. Okay, so that's how synthesis reactions work. You have two reactants and then you have a product. So for a chemical reaction, example of this, we have the combination to create water. Okay, I'm going to put this on the board just so I can help keep track of what's going on. So for a synthesis reaction, you have 2 or more reactants that come together to make a product. Okay, so that's how I like to identify a synthesis reaction, is it has only one product. That's the fastest way to identify it has one product. Okay, so when you're trying to identify reactions, that's a really quick way of doing it. Now that's totally opposite of decomposition, because decomposition is when you have something that breaks down, decomposes, breaks down into 2 or more compounds or atoms. So it's the direct opposite of synthesis or combination. So an example of this could be a shell breaking open and creating a broken shell, an empty broken shell, and then a fully grown tortoise, maybe? Fully grown turtle. I've seen baby turtles, they don't look like that. But you know, the idea is there. You had something that was all together combined ahead of time, and then it breaks apart into two or more things. In some cases, you might end up with 3 products from a decomposition reaction. One thing breaks into 2 or 3 or 4 products. And these are often an explosion, right? Because if you have one thing in the beginning, like a compact solid, and it breaks up into multiple things, that's going to take up more space. So what you had before was compact and small. Afterwards, it's 2, 3 things that might involve gases. And the rapid expansion of gases is an explosion. So decomposition reactions are mostly explosion reactions. And this one is the opposite of the example we saw before. So we have water breaking apart to hydrogen and oxygen. We've seen this in the lab before, back when we were in the lab together. We had to use the Hoffman apparatus, if you remember that, and electricity to break water apart. So this reaction doesn't happen on its own, thank goodness, because if it did, everything would be blowing up constantly. But the way I identify a decomposition reaction is it starts with one product, starts with one reactant. Okay, so when you're looking at identifying, again, on the homework, if you're looking at which ones are decomposition reactions, they start with one reactant. So they're pretty easy to spot because they only have one thing, and then you have the arrow following that. All right, single replacement is one of the most common types of reactions because you have one single thing that comes in and takes the place of another in a compound and kicks it out, basically. So my prom experience, right? Or maybe one of your prom experiences, I don't know, or dance. You think you're all that. You show up at the dance with a hot date, Mr. Goatee guy, and that female there. And you think you're all that, but then high water pants guy comes in with the cool shades, and your goatee just can't compete with that action. I'm sorry. So anyway, long story short, he ends up with the girl, and you're left to go home on your own. Okay. And this is really how chemical reactions work, because if something more attractive shows up, like, not attractive like, wow, that looks good. It's more like an actual physical pull because of the electrons, like you have a stronger attraction force. It will break off and recombine. So that's what single replacement reactions do. You have a single thing take the place of another in a compound. So in this case, the compound is a girl and boy partner at a dance, and something better shows up. She wants to be combined with that instead. So you're left out on loser street, going home by yourself. Zinc will do that. Okay, so let's look at this example. So this is a single replacement. Single replacement reactions, we have zinc coming in and reacting with hydrochloric acid. And afterwards, we have zinc chloride and hydrogen gas. So how do I quickly identify a single replacement reaction? I usually look for a single thing and a single thing. So you have a single thing before, and then afterwards you have a new single thing. Now I know technically the hydrogen is bonded with another hydrogen because it's H2, but it's still only hydrogen, so it counts as being displaced. Hydrogen has to be H2 just because of the way it is. We've learned about the molecular elements before. So the zinc takes its place and kicks it out. So you'll notice these reactions are already balanced too. So it makes it a little easier. All right, so single replacement is a single thing. You can probably guess what double replacement might be. It's when you do a double switch. So you have parts of two compounds switch places to form two new compounds. These are the most complicated looking reactions just because there's two things that move places and not like a single replacement where there's only one thing that moves in. So they double switch partners. I don't think this really happens at a dance. Well, from my personal experience. So we have these gentlemen here with hats. And we have big guy, big hat, little guy, little hat. After the reaction, they've switched hats. Okay, so same guy, different hats. And that's a representation of how double replacement reactions work. So in the case of an actual reaction, for double, I'll just say double R because these take up a lot of space. We have silver nitrate, AgNO3. And the AgNO3 is reacting with salt, NaCl. The Ag and the Na switch places, so we end up with AgCl and NaNO3. So hopefully you can see that, but the Ag and the Na just switch places. So it's an easy way to identify a double replacement reaction. What we're looking for here is 4 compounds, basically. Okay, because we have 2 before and 2 after. So double replacement reactions typically are the ones that have 4 compounds before and 4 after. They're also usually the hardest to balance just because they have so many parts to them. But that's the best way to identify those. So we have a subgroup of the double replacement reactions. We won't have time in this year to cover acid-base reactions. But we'll talk about them here so you know what's going on. Acid-base reactions are where an acid and a base will come together and neutralize one another to produce a like a benign product, salt and water. So in the case of our example here, you can see we have acid plus base gives you salt water. Kind of hard to tell what's going on exactly. So let's look at a chemical reaction, like an actual neutralization, this is called, reaction. So here's our acid base. And I have a story about this here, but so you have HCl plus NaOH. And it is a subtype of double replacement. So in double replacement, if you remember, the Na and the HCl switch, right? So they switch partners, and that's what happens here. So you end up with, on this side of the reaction, what way do we have it on there? You have H2O, okay? H2O because it's HOH. Like the H goes here with the OH, and it makes HOH. That's the same thing as H2O. But then you also have NaCl. Okay. NaCl is actual salt, right? So table salt. So you end up with salt and water with the acid-base reaction. So you have an acid, HCl is our acid, you have a base. After the reaction, you end up with water and salt. So that's kind of interesting that you can have something that would kill you and something that would kill you react together to make water and salt. So if done correctly, you can mix these together and make a totally fine thing to drink. I mean, salt water tastes pretty bad, but it's not like dangerous. So here's the story. There was an older chemistry teacher that used to work at the building, and he did this demonstration, which was pretty fantastic. He would measure out an exact amount of hydrochloric acid and an exact amount of NaOH, and he'd carefully balance it so that when he poured them together, it would make salt water. The salt water was safe to drink, obviously, and he would do so, you know, which is a no-no. You're not supposed to do that in the lab. But he would do it, and when he did so, he would run out of the room in a terrifying kind of way, and you know, scare the whole class like something went wrong, right? So he'd pour them together, you know, the acid, the base, pour them together, make salt water, presumably, drink it in front of the class and go, ah, and scream and like run out of the room. The whole class is like terrified that he's dead or something, and he's in the prep room screaming, you know, like it was burning his mouth. And he would don this mask, like this terrifying Halloween mask, and then he'd run back into the room and just yell, and everybody would, you know, scream like crazy. So I'm like, man, I want to do that. That sounds so cool to do something like that. But I didn't trust that I could measure. This is my problem. I couldn't trust that I would measure the acid and base correctly. So what I did instead is I put universal indicator in it. Okay, so you put just a couple drips of universal indicator in there, and the universal indicator tells you if it's safe or not, because acid is red, base is blue. If you mix them together correctly, the indicator changes to green. Okay, so the green says to me, hey, this is safe to drink. So I measured it out carefully. I took the acid and the base, I poured them into the container. They mixed together. From red, you could see, I added the red, take the blue, add the blue, it changes to green. And the whole class is like, oh, wow, you know, that must be neutralized now. And I'm like, okay, yeah. So I drink it, you know, because it's supposed to be salt water. I'm believing in the chemistry. And yeah, salt water. It was salt water, but as soon as it hit my mouth, I knew there was something wrong. It was the indicator. The universal indicator I used to double check my work was wicked poisonous, like very poisonous. It says on the container, like, can cause death, can cause blindness. Okay, it's got really bad chemicals in it. So it tasted awful. And it recommended inducing vomiting, you know, which I did because I like to be alive and I like to be able to see. I can't imagine being both dead and blind. That would be pretty awful. So anyway, so I did run out of the room terrified, and I did make sick noises in the prep room because I actually was sick and actually was terrified and dying. So I'm sure I didn't have a fatal amount, but you know, that's one of those things you definitely don't want in your system. So anyway, I don't do that demonstration anymore. You'll have to forgive me for not doing that. All right, let's look at the last reaction type. We are not covering naming acids in this notes today, just because we won't have time to do all that in this year because the end of the year is quickly approaching. And we're also going to skip some of these in the classroom as well because we only have 4 more weeks. So this week we're doing reaction types. And next week we'll do synthesis reactions. We're going to try to do synthesis, decomposition, and single replacement, because those kind of cover most of the ideas of the labs. So combustion, our last reaction type, is involving burning things, of course. And in the case of our lab, it's usually organic compounds that we're burning. So wood is a good example of that. But we do have, propane at our disposal at the lab stations, or butane, other organic compounds like that. And what you need is oxygen. Okay, so the oxygen is actually really important to these reactions. And having the right amount available allows your reaction to burn correctly. So we're going to use CH3OH, which is a propanol, and that's a oxygenated fuel, let's say, because it has oxygen built into it. It helps it burn a little better. It's going to react with our oxygen to create CO2 and H2O. So in a proper combustion reaction, we would always produce carbon dioxide. Now the water that's produced is actually a gas. So it's not like it's, splashing us in the face when we're burning something. But you might notice in a vehicle exhaust, sometimes it will drip water, condensation from the combustion reaction. That's normal. It does come out as a gas, but the exhaust is long enough that it condenses. So, but that's how combustion reactions work. So how do you identify a combustion reaction? I usually look for a CH and an O2. If it starts with a CH, typically if it starts with a CH, that's all you have to see, and that's a combustion reaction. If you see the O2 there as well, then it's gold and it has to be a combustion reaction. But that's how combustion reactions work. Now, if you start to run out of oxygen, you can't make CO2 anymore, so it makes CO. CO is carbon monoxide. That's a really poisonous gas. It's odorless, it's colorless, so you can't see it or anything like that. But it does, obviously affect you. It starves your body of oxygen, and you get headaches and everything like that. So you want to burn things in a well-ventilated area, basically. So, and the product can actually be carbon too. If you run out of even more oxygen, it doesn't even make carbon monoxide, it just makes carbon in water. Always makes water. And if there's plenty of oxygen, it makes carbon dioxide. If there's limited oxygen, it makes carbon monoxide. And if there's even less oxygen, then you just get carbon and water. Each of those has water, but just a different amount of oxygen connected to the carbon. So, but those are the reaction types. Now there's an in-class practice. I'm just going to put that up so you can see the answers to that. If you can check your work, just to make sure you can identify the reactions correctly here. Very nice animation on those. So, and the homework has balancing, but you don't have to do that. I just want you to be able to identify reaction types. And we're not covering naming acids, so you can leave the very bottom of that page blank for that and skip over the notes. I just want you to be able to identify the major reaction types, and so that's what we're focusing on this week. So, and yeah, like I said, what we're going to do for the rest of the year, for the next 4 weeks, is we're going to go to synthesis reactions, then we're going to do decomposition, and then we're going to do single replacement to help with understanding how reactions work. So for the homework, the big key parts are one product is synthesis, one reactant is decomposition, single thing to a new single thing is single replacement. 4 compounds, 1, 2, 3, 4, is a double replacement. But if it starts with an acid and a base, then it's a special type of double replacement known as an acid-base reaction. And then combustion reactions start with a CH and an O2, and the products kind of vary a little bit if you have a different amount of oxygen. All right, hopefully that was helpful, and we'll catch up with you guys soon.